record. All right. All right. So, we're continuing on with section 16.2, talking about a line. Oh, by the way, if you have the homework, please turn it in before you leave. There's, of course, brand new homework right there for you. Talking about line integrals, and so I've just put in the basic kind of formulas that we've developed so far. The first thing we have to do, we're talking about integrating over a smooth curve, and it's essential that we parameterize the curve in order to be able to evaluate the integral. So we have to have a parameterization of the curve from t going from some number to another number, and then when we figure out the integral, we integrate with respect to the parameter t from the lower number to the top number. We have to plug in our parameterization into our function, and then if we are integrating ds with respect to arc length, that's ds, we have to multiply by the square root of the dx dt squared plus dy dt squared. Now, if we are taking the integral with respect to either dx or dy, we then only multiply by the derivative of x or the derivative of y. So it's a shorter formula. And we went through a few examples of this last time. All right. So what we're going to look at next is the next big topic in this, and this is line integrals of vector fields. Vector fields. All right. Now, we had a couple of, at least one homework with this, and this is from physics, where we have this concept called work. And basically, work in I guess its simplest terms, is applying a force over a distance. I mean, that's the most basic way of looking at work. Applying a force over a distance. Okay. Now, what we had looked at previously, this is when we were studying the dot product. We had a constant force. The force was constant. All right. And we were moving an object from point P to point Q. Moving an object from P to Q. All right. And we had this formula for the work. The work involved, and we usually use a capital W to denote work, was the dot product of the force vector dot the distance vector. And this is the displacement vector. If we're going from P to Q, this is the vector, the displacement vector, which is Q minus P. All right. That is what the D was. Okay. And so basically what this means is that when we're applying a force to something and moving it and then going in a direction, the only part of the force that, shall we say, counts is the part of the force that is in the same direction as where we are moving. Okay, so when we do this dot product, that is only applying that part of the force along where we are moving. Maybe I can just do this. If we have a force F like this, and say we are moving and this is the displacement. We're moving along this direction, all right? We look at the dot product, so we have an angle alpha here. And remember that the dot product of F dot D, that's the magnitude of F times the magnitude of D times the cosine of the angle between them. So another way of writing this is the magnitude of the force times the cosine of that angle times the distance. Well, this thing right here, F, the magnitude of the force times the cosine, if we drop a perpendicular line down from the tip of the force vector, make it a 90-degree angle with the distance that we're moving, this portion of the force is what is being counted, which is this portion is, of course, the magnitude of the hypotenuse times the cosine of the angle. So it's only this part of the force that, shall we say, counts in the work that we do. The other part of the force just it's going at a 90-degree angle. It doesn't count. It doesn't help you in any way with going the distance. It's just in the wrong direction. Okay. Now, what we are talking about now is instead of the force being a constant, we're talking about a variable force field. Capital F. So what this is going to be represented by a vector with variables in it. Okay, so for each x and each y, we're going to have different values of the force. Okay, so it's a variable force field. And instead of just moving along a straight line, we're going to be moving this force along a curve, or applying the force along a curve. Apply the force along a curve. Capital C. All right. And this is going to involve an integral here. So let me show you this drawing. Okay, so here's our curve here that we're applying this force from. It's starting here and we're moving around, going there. So we're applying this force. And at every point, and this, by the way, looks like it's three-dimensional because we have an x, y, and a z. So at every point here, x, y, and z, we have a force field, capital F, and we plug in the x, y, and z, and that'll give us a vector that the force is moving, showing us the direction and magnitude of the force. All right. Now, the only part of that force that's going to count, we're talking about doing work here, and I have it written here, only the component of the force field that's in the direction of the curve is going to count in figuring the total work. So what we can do is this. So what vector does move in the direction of the line? It's the tangent vector. The tangent vector moves right, we draw right there on the line. It moves right there in the direction of the line. That's where it points to as to what direction we're headed in. So we take the tangent vector. In fact, we take the unit tangent vector. So that means it has magnitude equal 1. And we dot product it with our force. So we dot product that with our force, F dot T, and that'll give us the portion of the force. So I could take a line down that is that is perpendicular to my tangent vector, and only this small part of the force is what's going to actually count in the work, in calculating the work done. So what we end up doing here is this. We end up summing up a bunch of things. We take the dot product of our force with our unit tangent vector, F, so we have F dot T. And then we multiply them by the little bit of distance along the line that we're moving, which is a delta S as in Sam. We keep subdividing our curve into smaller and smaller segments, and we add all this stuff up. So the work is equal to the limit, as these segments go to infinity, of the sum of all of these little dot products times the distance. Okay, that gives us just the force that goes in the direction we're moving times the distance, which is what work is, force times distance. Well, this limit becomes the integral. So the work here is now a line, this is a line integral along our curve C, and what we are integrating now is this dot product. This is what we're integrating, F dot T. And then we're integrating with respect to the arc length, the S. All right. So what we're going to show in just a minute is a little bit better formula here that we can work with, okay, to calculate the work. All right. Remember, to work with any of these line integrals, we have to have a parameterization, all right, to be able to do the calculation. So what we do here now is we parameterize this. So let me rewrite this thing. So we have here work is equal to the line integral along our curve C of the dot product of the force with our unit tangent vector with respect to S. All right. So parameterize the curve. Okay. So let's have this, and let's look at three dimensions here. All right. So we're going to say that the curve is given by this, where we have some function x of t times the unit vector I plus some y of t times the unit vector j plus z of t times the unit vector k. Remember, this is the unit vector in the x direction, the y direction, and the z direction. Of course, another way of writing this is to use the bracket, that kind of notation, and this curve is represented by x of t, y of t, and z of t, like this, all right? Where t goes from A to B. Okay. Now, t up here, our unit vector, our unit tangent vector, rather, let's represent this with our parameterization. Okay. The unit tangent vector is this. We take the derivative of the curve vector. So I take the first derivative of my curve vector, and I have to divide it. I need to have a magnitude of 1. So I have to divide it by its magnitude. Okay. This gives us magnitude 1 by dividing it by its own magnitude. And this up on top here, this is the derivative of the curve vector. And that gives me my unit tangent vector. Now let's see what else was, so that's this part of it. Now ds, I'm going to replace ds like I did before with the square root of dx dt squared plus dy dt squared plus dz dt squared dt. I'll replace ds with that. All right. And then let's see, what does this actually equal here? This here, this part of the ds formula is actually the same as this right here. The derivative of the curve, of course, r prime of t, well, that's just equal to the derivative of each of the components, right? Derivative of the x component, derivative of the y component, derivative of the z component, all right? And then if I take the square root of the sum of the squares, that gives me the magnitude of this. So this part right here is the same as the magnitude of the derivative of the curve. So let me rewrite this ds then as in a much shorter manner as ds equals, now let me replace this whole big thing by the absolute value, or magnitude rather, of r prime of t, and then we have the dt after that. Okay. Now what I'm ready to do then is plug all of this new stuff into here, and I'm going to get the equation, the formula that we're going to work with, okay? So let me rewrite my original formula here. Integral of c f dot t ds, and we're going to replace that with this. Well, first of all, we're going to have our parameterization from a to b, all right? And then what I'm going to do here, I need to parameterize my function here. So I'm going to represent my force vector in terms of the t, and we'll see this when we do an example. So I need to plug in my parameterization into my force vector, and then we have a dot product. And then let me rewrite my unit tangent vector as what I had up here. That's going to be the derivative of my curve vector divided by the magnitude of the curve vector. So I'm replacing this with that, and then I'm replacing ds with what I have here, the magnitude of the derivative vector times dt. Okay, so I've replaced everything, and notice now that on the numerator and denominator on the inside, I've got the magnitude of r prime. So I can very nicely, because we're going to assume that doesn't equal 0, so I'm going to cancel that out, and I get this formula. W, or work, is equal to the integral from a to b of our force parameterized, so I'm putting in the r of t there, dot, these things canceled out, but it's dotted with the derivative of my curve, r prime of t, dt. So let me put asterisks there. Remember that on the test and on the final, you can use the cheat sheet, take front and back page so that's something I believe that you would certainly want to be including on that sheet, all right? Okay, now there's actually an abbreviation for this. The abbreviated way of writing this, so an abbreviated way of writing this, because mathematicians love to just abbreviate things into, so it's just easier to write, and then of course then it looks very mysterious then if you don't understand the abbreviation. Abbreviated as this, basically we have an integral over C of f dot dr, all right, like that. So that's an abbreviation for this thing right up here. All right. Now, let's do an example here so we can put some numbers into this formula. Example. Evaluate integral over C f dot dr, where, first of all, we better know what our f function is, where f of x, y, and z, remember this is a vector, is equal to the following: x times y times the I vector plus y times z times the j vector plus z times x times the k vector. And our curve C is given by this, because remember, we need to parameterize it. It's given by x equal to t, y equal to t squared, and z equal to t to the third power, where in this case, t is ranging from 0 to 1. This curve, I showed this one time in an example, I think it was last semester. There's actually a name for this. This is a three-dimensional curve, of course, and it's called a twisted cubic. That's not important for you to remember, but it had a kind of a funny, I showed different views of it, of what it looks like. All right. Now, okay, let's work this now. So remember, when you see something where it says evaluate this f dot dr, what it's really telling you to do is this thing right here. Okay, that's what it means. So first of all, we need to plug in our parameterization into our force function. That's one thing we're going to have to do. So f evaluated at RT, where we parameterize it, well, let's see what we have here. First of all, we have x times y. X is given by t, y is given by t squared. So this is going to be t times t squared, which of course will end up being t to the third power. And this is times the I vector, plus y times z. Y is t squared, z is t to the third, and that's times the j vector, plus z times x. Z is t to the third, x is t, so that's going to be t to the third times t, and that'll be times the k vector. All right. So another way of writing this, then, let's first of all simplify it. T times t squared is t to the third, is by using the bracket notation. So my first component is t cubed. Then we have t squared times t to the third. That's t to the fifth for my second component. And my third component is t3 times t to the first. That's t to the fourth. that's my parameterization of the force function. All right, and then what else do we need here? Let's look at our formula. So we've gotten that part of the integral. Now we have to dot product this with the derivative of our curve. So I need to calculate now R prime, or R arrow prime. Okay, so let's see. Well, first of all, let's actually look here. I really kind of skipped something here. We have the parameterization here, x, y, and z equals this. So that tells us that our curve function can be written like this, where we have, this represents a vector function for our curve. Let's just put the components. My first component is going to be t. My second component is y, which is t squared. My third component is t to the third power. So that's another way of representing our curve. Now, what I have to do here as part of our work is I have to get the derivative of the first derivative of that. So, derivative of t is 1. Derivative of t squared is 2t. Derivative of t cubed is 3t squared. All right. So, we're ready here to at least now write this down. Okay, what are our bounds of integration? A and B. We're told that t ranges from 0 to 1. So I put 0 and 1 there. And then we're going to dot product. So let me just write this. Let me just show the work here. We're dot product. Here's our f function with the parameterization. T to the third, comma, t to the fifth, comma, t to the fourth. That's our f. And we're dot producting that with our derivative of our curve. So that's 1, comma, 2t, comma, 3t squared. That's our derivative of the curve. And then we just put dt at the end. So do we remember how to do a dot product? How do we do that?
Isn't it x and x multiplied plus?
Yeah, you multiply the components together and add it all up. Okay, so that's how you do a dot product. So let's rewrite this with that. So we multiply t cubed by 1, so that's t cubed. T to the fifth by 2t, so that's 2t to the sixth. And then t to the fourth by 3t squared, that's 3t to the sixth power. All right. And then this is all dt. So actually we end up getting something that's very easy, hopefully, to integrate in this case. All I need to do, let's combine the t to the sixth terms, this 5t to the sixth, and do the antiderivative. So t to the third is going to be t to the fourth over 4. 5t to the sixth is going to be 5t to the seventh over 7. And my limits are from 0 to 1. So the bottom limit cancels out. I just have 1/4 plus 5/7, which combines over 28 to 27 over 28. And that's my answer then. Okay? So this is the general process here of doing these work things. We have to we've got to have our parameterization of the curve. We have to plug that parameterization into the given force vector that we're provided with. We then have to get the first derivative of the curve that we're given, dot product them together, and apply that, and then we have our limits of integration, whatever they are. Any question on this first example here of this? All right, let's look at another example here, just so that we get familiar with this. Example, find the work done by the force fields F of x, y. So now, this is now a two-dimensional example, all right? And what we're told it's equal to x squared times the I vector minus xy times the j vector. And let me just put another way of writing this then is use the brackets, x squared minus xy. And then what's our curve? Find the force done by the force field in moving a particle along the quarter circle given by r of t equals cosine of t times the I vector plus sine of t times the j vector. And this time we have t going from 0 to pi over 2. All right. So let's just make sure we're clear on what we're talking about here for this curve. It's a quarter circle. X is cosine, y is sine, and it goes from 0 degrees to 90 degrees. So this is going to be our curve right here. It's going to be a fourth of a circle, a fourth of the unit circle. Okay, that's our C. All right. So let's see here. So this is going to, so we're talking here about, let me rewrite R of t. I like to use the bracket notation. Is bracket cosine t comma sine t. All right. Okay, so first of all, we need to plug in our parameterization into the f function. So plug in the parameterization. Now this is our x and that's our y. So therefore our f is going to be what? First of all, it's x squared. So the first component is going to be cosine squared of t. And then it's minus xy, so that's going to be minus cosine of t times the sine of t. So we need to plug those in. And then we need to also calculate the derivative of our curve. So that's going to be what? Derivative of the cosine is the negative sine of t. Derivative of the sine is the cosine of t. All right? And then we're ready to set up our integral then. Our limits of integration here now are going to be 0 to pi over 2. All right. And we're going to, we're going to be dot producting the f with the r prime. So let's just go on and do that here. So we're going to multiply the first two components. So that's going to be minus sine t cosine squared of t. And then multiply the second component. That's going to be minus sine t, also cosine squared of t. Same thing, actually. And then we put in our dt. Okay, then we simplify as we can here with this thing. So they're both the same deal, so I can just write this as minus 2 times the sine of t cosine squared of t, dt. All right. So then it's a matter of integrating this, and we should all know that I'm going to do a u substitution with u equaling the cosine of t. So du is the negative sine of t. So notice we have negative sine and times dt also. So we've got negative sine t dt already there, so I can rewrite this as, I still have a 2 here though, so I have a 2, and then I have to put my u squared, and then my du, like that. Okay. I think I'll just go on and keep this in terms of u. If I do that, remember I've got to change my limits of integration. So I don't have to go back to t to figure this out. So first of all, when t is equal to 0, the cosine of 0 is 1. So u will be 1. And then the top one, when t is equal to pi over 2, the cosine of pi over 2 is 0. So it's going to be a 0. All right. Okay. So it's okay, and it is okay to have a smaller number as the upper limit of integration. All right. So let's just rewrite this then. We're going to have 1 on the bottom and 0 on the top, and we're just integrating 2u squared du. Okay. So that's going to be 2u to the third over 3 from 1 to 0. And then that's going to come out to be negative 2/3. Right? Okay. All right. So I think what you're going to find in this section is that the integrals themselves are not going to be tremendously difficult, I don't think, to get antiderivatives of. What's this trying to tell me? Oh, okay. Now, so that's the second example of this work thing. The very last thing then in this section, then we'll take a break, is that there is a connection between what did I call these, vector, how did I phrase it? Vector integrals, what did I call it? Yeah, between the line integrals of vector fields and, well, let's just call this, and the line integrals of scalar fields. And I'll explain what I'm talking about here in just a second. Okay, let's see what I'm talking about. Okay, let's talk about a vector field. Now, this doesn't have to be a force field, but I think it's more often that's what you're really talking about. But it really could just be any vector field, okay, where it changes as we go through the different points. So let this be represented by some function of x, y, and z, so we're talking about three-dimensional here, times the I vector, plus another function of x, y, and z times the j vector, plus r of x, y, and z times the k vector. So that's our force field or vector field. And then we saw that the line integral of f dot dr is equal to the following. It's equal to the integral from a to b of f, where we parameterize our f, so I plug in the r of t there, dot product r prime of t dt. Okay, that's the formula we just had. And let's write this a little bit differently then. What I'm going to do now is I'm going to plug in, I'm going to use my definition here, of the f function. So this is equal to the integral from a to b of, okay, right, let's do it this way. First of all, I'm gonna just use a little shorthand here of p times I plus q times j plus r times the k vector dot product that with r prime of t, which is going to be, okay, we have, which is the parameterization, x prime of t times the I vector plus y prime of t times the j plus z prime of t times the k vector, and that's dt. So this is really in bracket notation, our force is PQR with brackets, dot, and then our R prime is X prime, Y prime, and Z prime in brackets. And let's dot product this. So that means I'm going to multiply this by this, plus this times this, plus this times that. So that gives us from A to B of P times X prime of T plus Q times Y prime of T plus R times Z prime of T dt, like that. Okay. All right. Basically, this dt applies to all of these. So why don't I just put a dt after every single one here. And let's then look at what this is right here. What we have there is the following. Here we have x prime of t times dt. Well, x prime of t, another way of writing that is dx dt, the first derivative. And I'm multiplying that by dt. Remember, with these differentials, we can do this algebra on them. So that's the same as dx. So here I have a to b of p, our first component of the force, times dx. And then let's go to the second part. We have q, but now we have y prime of t dt, which is the same as dy dt times dt. Cancel out the dt's, pass the dy. And then the third one, we have plus r. And now it's z prime of t, which is dz dt times dt. Cancel those out, and that's a dz. All right. So basically, what we have is this. Let's kind of cut to the chase here. Conclusion. And this is something that you're going to use a little bit in the next section. So it's not just a kind of a, oh, here it is, and for what it's worth, but it is something we're going to use. So what I want to say with this then is this integral c of f dot dr. Assume that f is got the components p, q, and r. Okay, those are its three components. This equals the integral, the line integral along c of the first component there, dx, plus the second component, dy, plus the third component, r, dz. I think I'll put asterisks around that so that you guys make sure you remember that, all right? And this actually will come in handy in the next section. So what the deal is, this is kind of going from a vector to, let's just say, a kind of regular line integral. One is with respect to dx, the other is with respect to dy, the third one's with respect to dz. All right? Okay. And that, let's take a break. That closes out this section of 16.2. Okay. I don't want to keep you guys the entire time. Trying my best. I know that I'm hoping. Yeah. I'll just stop. Just somebody come up and just put a gag in my mouth or something like that. Okay. Okay. 16.3, the next section is titled The Fundamental Theorem of Line Integrals. Ooh. So that tells you from the title it should have something important in it. Some terrible, horrible calculations? Not really. Not really. I think you'll find calculations not too bad here. All right, first of all, you know from Calc 1, we've got this. If you take the integral from a to b of the derivative of something, that it is equal to the antiderivative of the top number minus the antiderivative of the bottom number, okay? So, antiderivative. So the nice thing about this is once you figured out the antiderivative, you only had to worry about the two end numbers. That's all you had to deal with. Well, we actually have a similar type of thing for line integrals. All right. So again, we're going to have, we have C as a smooth curve. It's parameterized by some function R of t. parameterized by r of t for t going from a to b, for a less than t less than b. All right, and let's say we can either here talk about 2D or 3D. It's going to be the same. So it doesn't, I mean, you can just extend it to one more dimension for 3 dimensions. Okay, so let a little f have first derivative. All right, so we're able to calculate its derivative. And so recall the gradient vector. For 2 dimensions, the gradient vector is f with respect to x, comma, f with respect to y. In 3 dimensions, it's f with respect to x, f with respect to y, f with respect to z. It's a vector. So, since this is a vector, we can treat it just like we did a force vector. Okay, it's a vector is a vector. Okay. So, fact, the line integral along this curve C of this gradient vector dot dr. So we're talking, this is just like the other one, except now we're replacing gradient f by what we had previously called capital F. That's all we're doing here. Guess what this equals? It equals to the original function f evaluated at the endpoint r of b minus the original function f evaluated at the beginning of our curve at a. So so we plug in the initial point, I'm sorry, this is the terminal point. We plug in the terminal point into little f minus plugging in the initial point. Plug in initial point. All right. We don't have to do any other calculations. This is it. Okay. So this is that fundamental theorem. So there are some similarities with how this works with how what you had learned in first semester, in the sense that you only have to deal with the 2 endpoints, and you can calculate your line integral. So this is a good thing. All right. So I think we should note this, okay, with an asterisk. All right. That's an important formula. Now, I mentioned this definition a couple sessions ago, but let me remind you of this. A reminder, or let me recall, shall we say? Recall a vector field, capital F, is called a conservative vector field if there is some function, we'll call it small f, such that our vector field f is equal to the gradient of that function. So we're going to see here that conservative vector fields are nice, because suppose F is a conservative vector field. Then, if we're doing this integral, f dot dr, Well, guess what? Since it's a conservative vector field, it equals the gradient of some function, dot dr, by definition. And therefore, we can very easily then evaluate this as f at the terminal point, little f at the terminal point, minus little f at the initial point. So conservative vector fields are nice. All right. Okay. Let's look at an example here of this. This is certainly a nice fact also to just keep in mind, okay, because we will be using that. Let's just look at an example before we go on. Example, let little f of x, y, and z equal 2xy times the cosine of z. Suppose C is a smooth curve with initial point, let's see, we're 3 dimensions, so 1, 2, pi, and terminal point, 3, 4, 2 pi. All right. Well, what we can derive at is this. Okay, let's get the gradient of f. All right. So we know the gradient is going to be a 3-component vector. The first one's going to be fx. Well, if I do fx here, I'm going to get what? Just 2y cosine of z. And then fy is going to be 2x cosine of z. And then fz, let's see, derivative of the cosine is the negative sign. I'm going to get minus 2xy sine of z. So that's my gradient. So we know from this fundamental theorem here that the line integral along C of my gradient 2y cosine z, 2x cosine z, minus 2xy sine of z dot dr is going to equal, well, this is my delta, my gradient of f dot dr. So it's going to be equal to my function little f evaluated at my terminal point, 3, 4, and 2 pi, terminal, minus my little f function at the initial point, 1, 2 pi. Notice in this case, I don't even specify what the curve is. All I'm saying is it's a smooth curve that starts at one point and ends at another, because I don't really need to be concerned about what the specific curve is, because all I need is the endpoints in order to evaluate this, okay? Because we're talking about the gradient of the f. So that's all I need. So let's just plug this in. Let's see, my function is 2xy cosine of z. So this is going to be 2 times 3 times 4 times the cosine of 2 pi minus let's see, 1, so it's going to be 2 times 1 times 2 times the cosine of pi, just plugging it in. All right, so what do we get here? 2 times 4 is 8, 2, 3, this is 24 times 1. Cosine of 2 pi is 1, so I have 24. Minus, and then we have 2 times 2 is 4. What's the cosine of pi, though? Negative 1. So I have a double negative, so I have a plus 4. So my integral evaluates as 28. Okay. All right. Now, this theorem holds even if our curve is a joining together of other smooth curves. So let me put it this way. This theorem is true if C is a piecewise smooth curve. So something like we can have C1 like this, and then we have some little point here, and then we have C2, another smooth curve, and then we have C3. All of the individual curves are smooth curves, and so it would work along this entire curve, okay? All right. All right. Now, the fact that all we need here are the two endpoints leads to this next kind of concept. The concept here is called independence of path. Okay, so if this theorem applies, say we have a point here, let's just call it P of X, Y, and Z. So we're talking about 3 dimensions here. And we have a point here, we'll call it Q of X, Y, and Z, some other point. No matter what my path is like, from Q to P, so my path could be like this, or it could be like this, or it could be more direct like this. All of those different, so these are called different paths. If that theorem applies, my integral value won't change at all because I have the same beginning point and the same end point. So therefore, we can say that the integral is independent of the path we're taking from one point to the next. All right, we'll get the same value for the integral. So in this case, we know that, say this is C1, and this is C2, and this is C3, we know that the integral of C1 gradient f dot r is going to be the integral of C2 gradient f dr, which is going to be the same as the value of integral C3 gradient f dr. All same values. Same beginning point, same end point. Okay. All right. So let's see here. Let me give you a more formal let's say independence of path means that the value of the line integral only depends on the two endpoints. Okay, does not matter how we get from one to the other. It only depends on the two endpoints. Okay. All right.
How do you look at something and know that this applies to it?
Okay. So in other words, how do you know that? Is your question, how do you know that? Well, let me see. Go on.
Well, with we're talking about the conservative vector.
Yes.
I feel how do you? I understand that the fourth vector equals the gradient vector, but I guess I don't understand how you recognize that.
Okay. Did I email you to ask that question? Because that is an excellent question. So no, it is. So your question is okay, it's really good to be a conservative vector field. How in the heck can I figure out whether something is a conservative vector field? Is there a relatively painless way to check for that? And there is. Okay, we haven't gotten to it yet, but there is. Okay, yes. So just hold on. Okay, but we might just get to that today. Yeah, we'll just get to that. Maybe we'll stop then. We'll stop on some good news and then go on next week. All right. All right. So I just want to say, maybe just complete to say, in other words, what I can say here is, i.e., let's do this way, i.e., integral C1 of, and we'll do it in general, f dot dr is equal to the integral along C2 of f dot dr as long as C1 and C2 have the same beginning and ending points, have the same beginning and ending or terminal points. Okay, that's what it means to be independent of path. So therefore, we know then that conservative vector fields are independent of path. All right. Are independent of path. Okay, all right. Almost there. Just a little bit of a sidetrack here. This will come more into the next section, but I just want to throw, first of all, a definition out. And it's a definition of what is called a closed curve. And I think it's just what you would think it is. A closed curve is one whose ending point is the same as its beginning point. Is one whose ending point equals its beginning point. So here we have a curve. We're starting out here. We're going around, and we're going to end right where we began. This is a closed curve. All right? Now, there's a couple of facts here that are connected with a closed curve. The line integral of f dot dr is independent of path, if and only if the line integral of f dot dr is equal to 0 for any closed curve C. And this kind of makes some sense here if you think about this. When we have a closed curve, the beginning point is the same as the end point. All right? So if we're talking about independence of path, we're talking about we only look at the beginning point, we only look at the end point. But if they're the same, when we apply those to our function, we get the same value for this one and the same value for this one. We subtract them, we get 0. So I'm hoping that that makes sense to you, that you can believe this. And so this is if and only if, which means that logically it goes in this direction and it goes in the other direction. Okay? So we're talking about any closed curve, our line integral equals 0. And then there's another fact that says this, and this, a vector field, capital F, is a conservative, and this isn't quite the good news that I talked about, we're getting there, is a conservative vector field if and only if its integral, line integral f dot dr is equal to 0. No. I'm sorry. If its line integral f dot dr along C, scratch out the equals 0, is independent of path. All right. Now, so the thing is, we still haven't arrived at your nice answer yet. Because, okay, we say a vector field is conservative if and only if, no matter what path we go from one point to another, we're going to get the same integral. Well, the thing is, you could go from here until the end of eternity figuring out different paths, and you still wouldn't hit every single path. Because there's an infinite number of paths from one point to another point. So this is not a very good way of recognizing what is a conservative vector field or not. But we have the next fact, which is the good thing. So let's say good fact. Capital F, and we're just talking about two dimensions. Capital Fxy, this is our vector field. Let's say that it breaks apart as p, some function of pxy times the vector I plus some function qxy times the vector j. Or another way I can write it with the bracket notation, pxy comma qxy. Okay, if we have this vector field is a conservative vector field if and only if the partial derivative of the first component with respect to y, dt dy, is equal to the partial derivative of the second component with respect to x. And this is the good test for determining whether a vector field of two dimensions, that we're just talking two dimensions, is a conservative vector field. All right. So I think what we'll start with then on Monday is we'll do a couple of examples showing that using this definition that a vector field is conservative, and then there's one other big topic in this section that will also, I think we might be able to do that also on Monday. Okay? So we are ending early. Let's circle this one on the calendar. Y'all have a good weekend. Okay? All right, you're welcome. Oh, how's it going, Nelson?
Pretty good. I'm at my homework again.
Oh, well.
I've been on the blues though, and people up here now.
That's great though. I mean, we pulled it out, right? I didn't say,
Well, homework, I picked up the last two Jacobian ones.
Oh, yeah? Jacobian?
Yeah, two last ones. I got the Jacobians, but not the,
Oh.
yeah.
Oh, this is where you actually have to do it.
Mm-hmm. Yeah.
Okay. Let's look at one. Let's look at one. Okay, I don't want to look at both of them. Okay, let's get this out.
I mean, I'm like my book on my phone.
Oh, no. This is 1510, I think. Yeah, 1510. Oh, great. Thanks. All right.
Exactly when you did in class, like the U was like it given or something.
Which one are we talking
8
about?
or 16.
8 or 16. All right, well, let's do 16, because 8 is, well, okay. 8 is S, U equals 0, I equals 1, B equals 0, 1, X equals B, Y equals U times 1 plus B squared, and we're asked to find the image of S. All right. Now, all right. So what we're asked to find then, this is in, so here, let's see, here we have, let's have U, we have V, U to 2, so this goes, it's just this little square right here, right? Okay. Now we want to find something in the XY plane. All right. Okay, let's see here. This is what we want. So, okay. X is equal to B. So let's do Y is equal to, and do we have any? Y is equal to, and this is U, right? Right. 1 plus X squared. All right. And U goes from 0 to 1. Okay. All right. X, first of all, X is equal to B. B goes from 0 to 1. So X is certainly going to go from 0 to 1. All right. Now, so this goes from 0 to 1. And this U also goes from 0 to 1. All right. So, let's look at, certainly when this is equal to 0, we're just talking about this. All right. And we're just talking about X going from 0 to 1. So here's 0. Let's go out a little bit. 1. Now, then when this is equal to 1, we have Y is equal to 1 plus X squared. All right. So here's, say, 1. And then, so we just go up from that, like this. And then, and let's go down like this. So wouldn't this point would then be, because we're going, this is 1, this would be 2, 1 comma 2. Okay. I'm thinking that that's it.
I'm the Jacobian.
Wait, isn't it just asking, is it just asking, it's just asking, find the image. Oh. Yeah. Mm-hmm. Right. Yeah. I think that's all it's asking for. Now, the other one, 16, is the tricky one. So we have 4x plus 8y dA. And I'm looking at the wrong problem?
Yeah.
Okay, here we go. The parallelogram. Minus 1, 3.
1 minus 3.
1 minus 3, okay.
3 minus 1.
3 minus 1 and 1, 5. And 1, 5, like this. Okay, so let me write these down. So this is 3 minus 1. This is
1 minus
1 minus 3. This is 1 comma 5. And this is minus 1 comma 3, right? Give me that. All right. So this is a parallelogram. What else do we have here? Well, we have our x is equal to 1/4 u plus v.
And y is 1/4 b minus 3 u.
What is it? V minus what?
B minus 3.
Okay. All right. So what we want to get here is, first of all, let's get the equation of these lines here. All right. So this one, let's see, a rise over the run, the difference of the y's is going to be a negative slope for one thing. Difference of y's is 6, and the difference of the x's is 2, right? So it's minus 3. And so it's going to be y is equal to minus 3x plus b, and let's just plug in this one here. So y is 5 minus 3 times 1 plus b. It looks like b is equal to 8.
Yeah.
Okay. So that's that. And this one is going to, let's see, we go, looks like we go over 2 and up 2, right? So our slope is going to be 1. And let's just do y is minus 3 equals x plus b. 1 plus b. So is it negative 4? And then this one is going to be same slope, yeah, y equals minus 3x plus b. So here we have 3 is equal to positive 3 plus b. Is that right? No, that can't be right. Wait a minute. Y is equal to 3. Oh, wait, yeah. Y is equal to 3. Oh, yeah, this thing must go through the origin. I bet this thing goes through the origin. Yeah. Okay, so this is y is equal to minus 3x. Yeah, when you look at it, that's what it is, right? Okay, and the last one then is this one here, where we have the slope y equals x plus b. And so y is 5 equals 1 plus, so b is 4 again? Yeah, here's the 4. Yeah, okay, alrighty. Now, let's see here. We need to get u in terms of x and y, v in terms of x and y, right? Yeah. So, nice thing here, this is going to work. This is going to work out. So let's just see what we get here. We get multiplied by 4. We have 4x equals u plus v. We have 4y is equal to 2. Is it minus 3u plus v? All right. Let's subtract. So let's see. These cancel out. This would be u plus, this would be 4u equals 4x minus 4y, right? Right. So u is equal to x minus y. All right. Now look at here. So let's circle this. And then we'll might as well just stop for the other one then too. So let's see here. Let's multiply by 3, right? Mm-hmm. So we get 12x, well, let's see, 3u plus 3v, 4y equals minus 3u plus v. So we have 4v is equal to 12x plus 4y. I think, Yep, so we have v is equal to 3x plus y. All right. Okay, so we look at this thing. We can change this one into 3x plus y equals 8. Right? This one into 3x plus y equals 0. And then this, of course, is v equals 8. V equals 0.
It's just like that example.
Yeah.
I tried to get them into U equals V equals, I was just
Yeah.
talking about it.
Oh, by this?
Yeah,
Yeah.
I didn't think of doing that.
Yeah, just, well, I'm teaching this in algebra, so, you know, that's nice byproduct. My algebra got a lot better after teaching it for about 4 years. Okay, so this is what do we have? X minus y, so this would be, is this x minus y equals -4?
Which is U equals.
Yeah, u equals, that's, u equals -4, and then we have x, and then here, this is gonna be u equals 4, right? Okay, so this thing converts over, so the region we're talking about then is a rectangle, right? If we have u and v, u goes from -4 to 4,
0 to 8.
and v goes from 0 to 8, all right? So this is what we're talking about. Let's see now, what else do we need to do? What's the deal here with this? So yes, I'm going to be integrating along this, which is easy. -4 to 4, 0 to 8. This is du dv. Now let's see here. Then we have to though get let's see the dv d. Actually here, then we use this for our Jacobian, because the Jacobian is going to be isn't it? dx du, dx dv, all that, okay? So let's figure out the Jacobian. So that's going to be 1/4 and 1/4, right? For that. And then this is going to be, I've got to be careful, this is going to be -3/4, right? Yeah. And then 1/4. So we get 1/16 double minus, remember, minus. Oh, yeah, right. Plus 3/16, so that's 4/16, which is 1/4. Okay. So actually here, we are integrating, wait a minute. Okay, those is a new, okay, so Jacobian, dxt, right, it's the Jacobian. So that'll be 1/4. And then du dv. Well, wait a minute, no, we've got to plug in our functions.
Oh, okay.
Yeah, right.
Just plug that in.
So, makes sense. So 4x is actually u plus v, all right. And 8y is how we done? Let me look at the book for a second, and then 8y is going to be twice that, right? So -6u plus 2v. Sure, we're following the formula right. And right, so we get our function in terms of u, v, and w, which is what we've done there. And we integrate along our new space in u and v times our Jacobian, an absolute value, but that's all right there. And this should be it then, right? So let's see, we get, so 4x u plus v, 8y minus 6u plus 2b, so this combines with what? Negative 5u plus 3b, and then we have a 1/4, like that. Okay, and then we do the integral with respect to u, do the limits, and then do the integral with respect to b. So that's just how that works out. So this is where you got stuck.
Yeah, I can't even think of that. I don't know why.
Yeah. All right. Did you do anything with this?
I started finding my slopes, but then I realized I didn't know how to get to that.
Okay. All right. Good eight.
I think about that.
Yeah. But that all. You're welcome. Sorry.
But I can probably create it, so. Wow. Sorry.
Well, that'll be great. I probably won't actually. I'll probably just create something on this section in which we just calculate something. Something like that. Yeah. Charles, how goes it?
Good question. Cool question. So on number 8, the intersection, the integral comes out to this, which I don't know how to integrate. Unless there's something wrong with that, but I don't know where it will happen.
This is in section 15.7.
Yes.
All right.
You can't change the order of integration because, as far as I can tell, because
That's right, exactly. Gotcha. So we're kind of stuck with this. All right, so here we're integrating with respect to y, so you get the minus cosine. And then wait, now here, cosine, okay, so we're plugging.
I'd work better if it's minus, because I'm moderating. 0 square root of pi. 0 to x. 0 to x. The is x squared sine y. Okay, so let's see. So here that's going to give us the sine and it's negative cosine. And then we have the x squared. And we're going from 0 to xz, all right? So that's minus x squared cosine of xz, and then we have the cosine of 0, so that'll be plus minus minus, so we have plus x squared. Is that what you have?
Yes.
You took out the x squared.
Yeah.
Right. And then we're integrating 0, this is 0 to x, and then that's dz, and then 0 to the square root of pi, and that's dx. All right. So this is the integral with respect to z. So the thing is, since we're integrating with respect to z, we can, right, this is the concept. getting messed up. So this X is a constant here. So basically, this is going to be, that's just a constant.
Right.
Let's see, that's going to be the derivative of the sine of the cosine.
No, that's like, what I meant is,
Divided by the constant in front.
that's what I'm saying.
Yeah, right, divided by the constant in front, and then plus x squared z, right? And then that's z equals 0 to x, right? Yeah.
Okay.
Yeah, so this one then, this will give us that minus x
Right.
sine of x times,
Side of x squared.
oh, wait a minute, that should be, yeah, right, exactly, right. Sine of x squared, and that'll work out there, that'll work out fine then, with,
Right.
yeah.
Okay. My next question was on number 30, this is 8. So everything worked out really well, but, so I looked up, like, and some of the questions have, like, solutions on the internet, so I was like, looking at them.
Oh, they at the end of it.
But that's right, I think you have a different solution from the correct one, so I want to double check that with.
Oh, let's see, well, let me see here, I can get, let me first of all just, it won't take me but a couple minutes to get us the solutions. What section was that again?
15.8, number 38.
Yeah. What?
That my homework right there? Is it good?
What?
To turn that in?
Oh, you're turning in the,
Yeah,
this is the homework due today?
I think so.
Yeah. Are you finished with it?
Yeah, except for those two.
All right.
Unless you want me.
No, that's fine. Did you do Jacobians? Okay,
Yeah.
good. Yeah, that's fine. All right.
I just want to like, I'm sitting there, I know some.
And have it sitting there, and then all of a sudden I just throw everything into the waste can, right, along with your homework?
Yeah.
Yeah. Okay. Have a good weekend. You too. All right. You're in that same linear algebra class.
Yeah.
Jim. He showed me some of the homework the other day.
Yeah.
I was actually surprised at sophomore level linear algebra class having some of that homework.
So that's why I was going over this, like, we should go. So the question has, on top of that.
Yeah, yeah. And Harry says he's very friendly.
Right.
And all that good stuff.
Very good, like, very good way to talk, like.
Yeah, yeah.
Also, you remember that, Rich mentioned that problem, that where you were like doing the inverse over Z3. He talked to you about it in class, I know, but, you might not remember.
Oh, yes, I remember that.
Like,
Yeah.
I'm actually in a programming class where you learn how to program apps on Android, so I was going to, I ended up, like, it wasn't so much that it was hard to do once you figure out what Z3 actually meant, but it was hard to, like, do all the, like, arithmetic because, we transfer out, like, it's easy to, like, you fall back into doing it with normal. Right. I'm hoping to write an app, like, to do, like, arithmetic of it.
Oh, yeah.
But, like, I don't exactly remember what like, that process is actually called, so I'm gonna go ahead.
Isn't that modular arithmetic?
It's just called my drug.
Yeah, I think so.
Okay, there's probably an app for that already. There are these apps for that, but.
Oh. All right, document. Solution. 15.8, where are we? There's 8. All right, what number were we? Number 3. Well, let's hear one. We want to just compare what steps and see where you might be differing here from this. Are you able to read that from here? Above the below that, to that, and then next.
It's from ours.
Oh, right, the RDR thing, right, for this thing right here, then, right, yeah.
Okay, all right, good. Oh, I have another one. So number 26 and 15.9 comes up to 0, which I guess could be the answer, but I just want to make sure that.
Number which again, sorry.
Yes, 0. Okay. We'd like to speak about the